This is for exercise 6C, the area of a sector of a circle. So if we have a quick circle, the centre 0, and a minor sector with an angle of theta radians, centre, and we're interested in finding the area of this minor sector. Remember, the radius of the circle will be r, because we're just looking at a general circle. Alright, now as a reminder from previous years, this should be burnt into your memory now, the area of a circle is pi r squared, remember. And then we're going to do a similar thing to what we did on exercise 6b, when we looked at the length of an arc. We're going to take the area of that sector, which we call A for area, and divide it by the area of the entire circle. So we look at the proportion of that area of that sector compared to the area of the entire circle. So that's be A divided by pi r squared, and that will be equal to that same proportion we get if we take the angle, which is forming the sector, and divide that by the full turn angle, which we know is 2 pi radians. So that's going to be the same as the proportion of theta divided by 2 pi. So we take the pi r squared, take it across the other side. So that leaves us then with a formula, just move these out of the way. That'll leave us then with a formula for the area of a sector. So that's going to be, take the pi r squared across, so we've got A is going to be equal to theta over 2 pi multiplied by pi r squared. So the pi's can cancel. Okay, if we bring that 2 out as well, we can tidy that up a little bit. That gives us a general formula for the area of a sector. So it would be a half of r squared theta. If we just simplify what was above. And that's what we're going to use with the problems we're going to solve in exercise 6C. Okay? Right, so let's do 2 examples then. I want to find the area of the shaded sectors of the circles I'm going to draw. Okay, so let's start with the big one. We'll have a circle with centre 0. Let's draw a sector there. So that's been subtended by an angle of 0.6 radians. The radius is 8 centimetres, so we just label that on. And I just want to find the area of the minor sector. So that's going to be the smaller, so that'll be like the pizza slice shape. Okay? So all I do is just recall that formula we looked at in the previous slide. Okay, so that's going to be, area is going to be a half times r squared theta. So if we just, r is going to be 8, theta is 0.6, so we just plug that into a formula. So that's going to be 8 squared, 0.6. If you work that out then on our calculator, that'll give us 19.2 centimetres squared, and I've rounded that to 3 significant figures. Okay? Job done. Now imagine if we had a different question, so we'll use the same numbers, but this time I'm interested in finding the area of the major sector. So that's like that little Pac-Man shape which I've just shaded there. So I need to find that angle there, which I was just pointing at. Okay? So just to remind you, that is the minor sector, the small one, and then the bigger one would be the major sector. So whenever you split, take a slice of a circle, you get a major sector and a minor sector. So if we've been given the angle for the minor sector, so we need to find the angle of the major sector. So remember, it's 2 pi radians in a full turn. So if we do 2 pi take away 0.6, that'll give us the angle of the major sector. Now let's not bother working that out because that's just going to give us a long decimal number. To be more efficient for us, just to put 2 pi minus 0.6 into our formula. So our formula for the area would be a half times 8 squared times 2 pi minus 0.6, and I just type all that into your calculator. Okay? So the answer we're going to get is 181.86102 blah, blah. Okay, and then obviously you'd round that to whatever degree of accuracy the question's asking you. So in this case, we just round it to 181.9 centimetres squared. Okay, let's round it to 1 decimal place. And that's it. We don't have to worry too much about our calculator being in radians or degree mode at the moment, because we're not actually using any trigonometry, we're just using that formula. So whether it's in degree or radian mode doesn't affect anything at the moment, but it is a good idea, as we're working with radians, to have your calculator in radian mode anyway, just in case you get a question where you are going to be using a bit of trigonometry. All right, so let's have a look at the next bit. Right, so before we move on to something a little bit harder, I just want to look at these two questions from question 1, okay? Because you haven't been given any information about the angles at the centre, so it's a bit more of a problem-solving aspect of these questions. To find that area there, we need this angle, okay? And to find that angle, we're going to need this one, all right? And it doesn't look like we've been given enough information. Now, we've got a radius is 4, because it's going from the centre to the circumference, so that must be 4 as well, okay? So we've got an equilateral triangle there, all right? So you might already have realised what that angle is going to be, okay? In degrees, it'd be easy. It's just going to be 60 degrees, isn't it? Because if all the sides are equal, then all the angles must be equal. So 180 degrees divided by 3 is 60 degrees, all right? Now, there's different ways you can think of in terms of radians with this. 180 degrees is the same as pi radians, so pi divided by 3 would give us pi over 3, or a third pi. Alternatively, we could just use that conversion fraction that we were doing in the first exercise and multiply 60 by pi over 180, and that would simplify down to pi over 3 as well, or a third pi. Okay? So that angle on the right is pi over 3. All right? Let's just label that. So we know in a straight line, in degrees, that would be 180 degrees. So in radians, that's pi. So that angle there is going to be pi take away pi over 3. Or think of it as 1 take away a third. All right? No, just put that in the corner. That's always a handy thing to remember. Pi is equal to 180 degrees. So our area then of that shaded segment is going to be a half r squared theta. So that'll be a half 4 squared times pi minus pi over 3. I'll just stick all of that into your calculator. Or work out pi minus pi over 3, which is 2 pi over 3 first, if you want to. But just plug all that into your calculator, let the calculators do the work for you, and then you get an answer 16.75516082, and then round that to the degree of accuracy the question is asking for. Okay? And part F is a little bit tricky as well. If you without an example for it really. So again, we need that angle there. Okay? We know that pi is 180 degrees, so that triangle on the left, all those angles add up to pi. We know it's an isosceles triangle because it's made up of two radii. So if we do pi take away 0.2 plus 0.2, just pi take away 0.4, that angle there, which we need, is going to be pi take away 0.4, so it leaves us with 0.4 radians. And then once we've worked that out, the rest is dead easy. I'm just going to use the formula and substitute theta will be 0.4, and your radius obviously is going to be 5. Okay, so I'll leave you to do the rest of that one. Okay, now exercise 6c then extends to finding the area of a segment of a circle and gives another formula for finding that. So I just want to go through where that formula comes from. All right? So if you've got a sector touching the circumference at A and B, so we've got a chord AB, which is going to be a straight line from A to B, and then the area between that chord and the circumference is called a segment. Okay? There's a difference between a segment and a sector. A sector is like a pizza slice or a cake slice. A segment is just like the crust being chopped off the side. Well, that's my year 9s, remember it. And then we've got the radius is labelled as well. All right. Now, obviously, we've got a non-right angled triangle there. We're going to use a bit of chapter 2 from core. So first of all, the area of a sector, we know, because we've just been working on that. So the area of the sector AOB is a half r squared theta. So we've just been working with that. Okay. So if you want to find the area of that segment, okay, we could take the area of the sector, which is that big slice, take away the area of the triangle, and that will leave us with that yellow shaded section. So we're going to need a bit from chapter 2 in core, and that was the area of a triangle. All right, if we worked out the area of a triangle is a half AB sine C. Okay, so we're going to call upon that. All right, so if you apply that to that diagram we've got there in the left, all right, the A and the B will be R, and C, which would be the angle in between them, is going to be theta. So in our diagram here, the area of triangle AOB is going to be a half r squared sine theta. All right. So as I said then, what we're going to do to find the area of the segment, we're going to take the area of the sector and take away the area of the triangle. Okay, so the area of the sector, the area of the segment, I should say. Sorry, get my sectors and segments mixed up. So that's going to be the area of the sector, half r squared theta, take away the area of the triangle, which is half r squared sine theta. Okay, and that looks a bit messy at the moment, but we've got a half common in the both terms. We've got an r squared common in the both terms. Looks like we've got a theta common in the both terms, but we haven't, remember, because on the left-hand side we've got theta. On the other side, that theta is embedded inside sine, so we have to treat them differently. So if we factorise it, we can take out the half r squared, okay, and then the theta and the sine theta will have to go into the bracket. So we've got half r squared, brackets, theta minus sine theta. Okay. Now, if you're going to use this formula, so because it's got sine in it, this is one that is vital that you have your calculator in radians mode. If you don't have your calculator in radians mode in this one, even with the correct working and correct method, it's going to be wrong because it's calling up the wrong values. It'll be calling up degree values instead of radian values. So at this point, before we go on to the next example, make sure your calculator is in radian mode. So finally then, this last example before you can get on with exercise 6C. So we've got a chord AB subtends an angle of 0.8 radians at the centre 0 of a circle of radius 6.5 centimetres. Find the area of the segment enclosed by the chord AB and the minor arc AB. Okay, so we're looking at the minor arc, so we're looking at the slice bit, not the Pac-Man shaped bit. Alright, so label them AB. Okay. So the arc is that there. So that's the minor arc AB. That's the major arc AB. So we're interested in the minor arc AB. And then if we draw a straight line from A to B, that's the chord AB. So the segment enclosed by the chord AB and the minor arc AB will be that yellow shaded shape there. Okay? And then we just plug that into our formula that we've just looked at, which is area, is going to be equal to a half r squared brackets theta minus sine theta. So it's very similar to the sector one we looked at the start. Instead of having half r squared theta, you've got half r squared theta minus sine theta. So put the values into that. You're going to have a half bracket 6.5 squared 0.8 minus sine 0.8. So if you haven't yet, pause the video and put your calculator into radian mode. Okay. If you can't remember how to do that, call up the video from exercise 6A, and that will, I've got a little video on the last slide there towards the end of the video that shows you how to do that in your calculators, if you've got the same calculator as me, obviously. So I can't emphasize this enough. You have to be in radians mode. What I'd recommend you to do, as soon as a question is on about radians, is, even if you're not going to use sine or cos or tan, make sure that your calculator is in radian mode straight away. So stick it onto your calculator, and if it's in radian mode, you should get this as your answer, 1.74585258. And then you're going to want to round that to whatever the question's asking. So let's round it to 3 significant figures. So it's 1.75 centimeters squared. Okay, done. Easy stuff. Right, answer the easy questions on show B and get on with the easier questions on exercise 6C. And in class, we can concentrate on the tougher ones. Okay, good luck.